Today we are going to talk about database design. Design has two components, logical design and the physical design. The main difference here is in logical design, we are designing a database that's technology independent. It means it doesn't depend on any one particular database management system, doesn't depend on one particular vendor or a particular programming language or technology. We just want to create a database design that's going to meet our business requirements. So that's the objective of the logical database design. In the physical database design, we are going to take into consideration the DBMS we are going to use, the vendor, the software, the programming language, and our focus is to improve the performance of the database as much as we can. So that's the main difference between these two different types of design. In this chapter, we are going to talk about logical database designs. In this phase, there are two main activities you need to perform. One is to transform the ER diagrams into relational tables. The second main task in this phase is normalization, which means converting large tables into smaller, well-structured tables. So those are the main topics that we are going to cover in this chapter. This book is focusing on relational database. All the databases in this class are relational database. A relation is a named two-dimensional table of data. That's the name they call a table in relational database. A table consists of rows and columns. There are a number of requirements for a table to qualify as a relation in the relational database. First of all, it must have a unique name. Within the same database, you cannot have two tables that have the same name. The second requirement is that every attribute value must be atomic. That means that you cannot have multi-valued attributes. For example, if you have an attribute called skills, you cannot have within a cell typing, access together, because then it's not atomic. The third requirement is that every row must be unique. In a database table, for example, student table, each row in the student table must be unique. It's unique because there is a primary key that's unique for every record. The fourth requirement is that attributes in tables must have unique names. Every field in this table must have a unique name. You cannot have two fields with the same name. The next requirement is that the order of the column must be irrelevant. That means you can switch the places of different columns and it wouldn't make a difference to the table. You can have the student ID as the first field, or you can have student zip code as the first field. It doesn't matter in a relational table. And also the order of the rows must be irrelevant. So you can move these records up and down and it shouldn't make a difference to the table. Those are some of the requirements to qualify a table as a relation in the relational database. In the relational database, there are three components. The first component is the relational data structure. That describes how the data is organized in the database. Talks about things like tables, attributes, and relationships between the tables. The second component is called the data manipulation, and that's referring to SQL that we are going to talk about in this class. SQL is the generic language for manipulating data in a database. And the third component of the relational database is called data integrity. That means implementing business rules to maintain the integrity of data when the data is manipulated. Here in red letters, it says all relations are in first normal form. This has to do with the other activity that's involved in the logical database design, which is normalization. All tables that qualify as a relation are already in the first normal form. And we will talk about what the normal form is in another slide, so don't worry about this for now. Let's talk about how to transform ER diagrams into relations. Here are some general rules. Relations or tables correspond with entity types and with many-to-many relationship types. What it means is that if you see an entity type in the ER diagram, a rectangular box, then it will be transformed into a relation or a table. So if you see student entity type, that means this will be translated into a student table in the database. The many-to-many relationship types will also correspond with a table. If you see a many-to-many relationship or an associative entity, that will become a table as well. If you see an ER diagram that looks like this, two entity types with a many-to-many relationship, how many tables would you get? 3, because one for each entity type and one for the many-to-many relationship. And then the second general rule is that rows correspond with entity instances and with many-to-many relationship instances. So each row in a database table is referring to an instance of the entity type. The last general rule is columns correspond with attributes. So each column in a database table is referring to each attribute that's in the ER diagram. For each relational table, you must have a key field, which is called primary key. A primary key is a field that uniquely identifies each and every row in the table. For example, student ID, that's different for every student in the table. So that's a primary key. There is another term called foreign key. Foreign keys are primary keys of another table. For example, you have two entity types. One is called customer, the other is called order. In the customer table, you have customer ID as the primary key. In the order table, you have order ID as the primary key. And then you have maybe order date and other non-key attributes. You probably also want to record who placed the order. So you probably want to include the customer ID in the order table also to record who placed the order. So the customer ID in the order table is not a primary key, it's a foreign key. The reason is because the customer ID field is a primary key in the customer table. So if the field is a primary key in another table, then that field is a foreign key. And usually we use dashed underline to show that it's a foreign key. The key can be a simple key or can be a composite key. So the foreign key doesn't have to be just a simple foreign key. It can be a composite foreign key as well, which means it may have multiple fields. The keys are usually used as indexes to speed up the response to user queries because the keys are usually what we use to search. So usually we will index these fields. This slide shows you some examples of primary keys and foreign keys between customer and order. Customer ID is the primary key, and the customer ID in the order table is a foreign key. Order line table's primary key is a composite primary key. It's the order ID field and the product ID field. And also at the same time, the order ID field is also the primary key of the order table, and the product ID field is the primary key of the product tables. The order ID field and the product ID field in the order line table, they are both the primary keys for this table and the foreign keys in this table. In relational data model, there are a number of constraints that you can create to ensure the integrity of the data in the table. The first type of constraint you can create in the relational table is something called the domain constraint. And that refers to allowable values for an attribute. For example, for the gender field, you can allow male and female. Maybe there is a certain range of numbers that's allowed in this field. That's called a domain constraint. Entity integrity refers to the rule that no primary key attribute may be null, so you must have a value for the primary key attribute. And then there are also action assertions that we talked about in the previous chapter, which are the business rules that can be used to put certain integrity constraints on data. This picture shows you the domain constraints for fields. For example, for the customer ID field, the domain is character size 5, which means you can have 5 numbers in the customer ID. For standard price, the domain is monetary, 6 digits, cannot have more than 6 digits. For order date, the domain constraint is that the date format is 2 digits for the month, 2 digits for the day, and 2 digits for the year. So those are some of the domain constraints you can put on the database where you create the database structure. And when users enter data into the database, if they enter 6 digits for the customer ID, then the DBMS is going to say, well, you entered an invalid customer ID, right, because of the domain constraint. So that's one way for the DBMS to make sure that the data has high integrity. Another integrity constraint that's very important in relational database is called the referential integrity. That means that any foreign key value must match a primary key value in the relation of the one side in a one-to-many relationship. For example, if we have two tables, one is the customer table, the other is the order table, and they have a one-to-many relationship, and the one side is customer and the many side is order. There is a foreign key on the many side in the order table, customer ID, and the primary key, customer ID, is in the customer table here. So what referential integrity means is that if you have a value of customer ID in the order table, let's say 001, okay, you must have a corresponding value in the customer ID field in the customer table, 001. If you don't find the 001 in the customer table, then it violates the referential integrity. Why is this important? Well, the reason is because sometimes you may want to find out who is the person who placed the order. If you cannot find the customer ID 001 in the customer table, then it doesn't give us information about the customer who placed the order. The information is missing here. How do you deal with referential integrity if you want to delete certain records? For example, you want to delete certain customers from the customer table because these are no longer our customers. If you have a customer 001 John Smith, however, John Smith is no longer our customer. Now you want to delete this record from the customer table. Well, so what are you going to do with all the records in the order table that has the customer ID 001? You have to make a decision about what to do with this record. There are three different choices. The first is to restrict, which means if you try to delete the record of John Smith and there is corresponding records in the order table, then the DBMS is going to restrict you from deleting John Smith's record. The second is called a cascade, which means if you delete the information on John Smith, then all the records related to John Smith in the order table will also be deleted. The last option is called set to none. What it means is, well, if you delete the record of John Smith in the customer table, then the customer ID of all the John Smith's order wouldn't have a value. It will have no value in it. So these are the three options you can choose in the DBMS to deal with the referential integrity issue. In most cases, restrict is the choice people use. More rules about transforming ER diagrams into relations. When you see a simple attribute, like last name, first name, the attribute maps directly onto the relation as a field. And if you see a composite attribute, for example, address, and within address you have street address, city, state, and zip, you use only their simple component attributes. When you translate that attribute into tables, you only put street address, city, state, zip instead of putting address in the table. And then if you see multi-valued attribute like skills, it becomes a separate relation with a foreign key taken from the superior entity. When you see a multi-valued attribute like skills here, you create a new table for the multi-valued attribute. Now you have two tables. You have an employee table and you have an employee skill table. And in the employee skill table, you're going to take the primary key of the superior table, which is the employee table, as part of the primary key of this table. So employee ID is part of the primary key, and then you add the skill field to be part of the primary key also, because employee ID may not be unique enough in this table. The same employee may have multiple skills. So when you see a multi-valued attribute, make sure you create a table for it. Rules about weak entities. If you see a weak entity like dependent, a weak entity becomes a separate relation with the foreign key taken from the superior entity. And the primary key of the weak entity composed of a partial identifier of weak entity and the primary key of identifying relation. Let's take a look at this example here. We have two entity types, employee and the dependent. And the dependent here is a weak entity. And the relationship is the identifying relationship. You will translate the weak entity into a relation, dependent. You are going to take the primary key of the superior table, the strong entity type, as part of the primary key of the weak entity. So as you can see, employee ID becomes part of the primary key in the dependent table. But employee ID alone wouldn't be unique enough because one employee may have multiple dependents, right? So that's why we also need to use the first name, last name, and middle name of the dependent as part of the primary key. So these 4 fields together will become unique enough for this table. Here are the rules about mapping binary relationships. If you see a one-to-many relationship, then the primary key on the one side becomes a foreign key on the many side. Let's take a look at an example here. Customer and order, that's a one-to-many relationship. You see 2 entity types here, so you create 2 tables. And then you see a one-to-many relationship, then it means that the primary key of the one side is going to be the foreign key of the many side. So that's why the customer ID is going to be the foreign key in the order table. The second rule about binary relationship is that if you see a many-to-many relationship, then you create a new relation with the primary keys of the 2 entities as its primary key. Let's take a look at an example here. In this case, we have a many-to-many binary relationship, employee and course. We see 2 entity types, and then we see a many-to-many relationship, so we create 3 tables. As you can see, we have 3 tables here. One is called employee, the other is called course, and then the many-to-many relationship becomes the certificate table. And also, we will take the primary keys from these 2 tables to be the primary key of the certificate table. So that's the rule for dealing with many-to-many relationship. If there is a one-to-one relationship, then the primary key on the mandatory side becomes a foreign key on the optional side. So let's take a look at an example here. In this case here, we have 2 entity types. One is nurse, the other is care center. One nurse is in charge of one care center or not in charge of any care centers. Here we have mandatory one on the nurse side, and we have an optional one on the care center side. Since we see 2 entity types, we are going to create 2 tables. One is called nurse and the other is called care center. And then, because this is a one-to-one relationship and the nurse is on the mandatory side and the care center is on the optional side, so the primary key of the mandatory side becomes a foreign key in the optional side. And just to make the name more descriptive, we are going to say nurse in charge instead of nurse ID here, right? Because this is really the ID of the nurse who's in charge of the care center. So that's how you handle the one-to-one relationship. So how do you map associative entity? There are 2 situations. The first situation is when the identifier is not assigned. When you have an associative entity, obviously you will create another table. And in this table, if the identifier is not assigned, then the default primary key for the associative entity is composed of the primary keys of the 2 entities, just like in a many-to-many relationship. Then the other situation is when the identifier is assigned. If there is a natural and a familiar identifier to end users, then you probably should use that as the identifier. The default identifier is referring to the combination of the primary keys of the other 2 entities. In those situations, the default identifier may not be unique. Then you probably need to assign the identifier. So let's look at some examples here. In this case, we have an associative entity called order line. That's the associative entity between order and the product. We see 2 entities. In an associative entity, we create 3 tables. The order table, the product table, and then order line table for the associative entity. And the primary key for the associative entity composed of the primary keys from the order table and the primary key from the product table. Product ID and order ID together becomes the primary key. This is the case when the identifier is not assigned. Let's look at another example here. In this case, the associative entity here is shipment. We create 3 tables: customer, vendor, and the shipment. By default, we should use the customer ID and the vendor ID together as the primary key for the associative entity. However, in this case, the combination of customer ID and the vendor ID wouldn't be unique enough because the same customer may order from the same vendor multiple times. So the combination here wouldn't be unique enough. So what do? Well, you assign an identifier. Well, for most shipments, there is usually a shipment ID. So that's why we create a new field here called shipment ID, which is supposed to be unique for every shipment. We use shipment ID as the primary key and use the customer ID and the vendor ID as the foreign keys. So that's the other situation when the identifier is assigned.